Okay, we're going to have a little screencast here, hopefully a little shorter, on wave interference and superposition, just kind of pulling everything together. We've talked about Young's double slit experiment in our last screencast, so this is kind of going to reinforce what you've already learned and then give you a qualitative and quantitative practice before your Mastering Physics assignment that's due on Monday. So just to reiterate the results of Young's double slit experiment, they're explained. The whole concept of Young's double slit experiment is based on wave interference. Two different sources, they interfere, and because of superposition, the superposition principle, there's points on a screen that are a certain distance away. I called it L, that there are locations where two crests or two troughs interfere and have constructive interference, and then there's other areas that have total destructive interference that a crest and a trough meet at the same time at that point on the screen consistently, and because of superposition they exactly cancel each other out and you get no intensity there. You get just a dark spot. It doesn't alternate between bright and dark as you look at it. It's just constantly dark at the dark fringes, and the bright areas, the bright fringes, are constantly bright because you either have a crest or a trough constructively interfering in those locations. So that's kind of a qualitative review. Again, we talked about in the last screencast, we developed quantitatively some equations, some relationships. We've got the sine of the angle is equal to the sine of the angle is equal to m, which remember m can be anything from 0 to 1 to any integer. And the lower that integer, the brighter the spot's going to be, more intense. And based on the geometry at the same time, you've got over here that the tangent of that same angle is equal to y over L. And as long as that angle is less than or equal to about 10 degrees, then you've got the small angle approximation where sine of theta is equal to tangent of theta, and you can set those two sides equal to each other. And that's where we came up with the Young's equation right there. Well, let's see what that looks like qualitatively, and we're going to actually change the spacing of D qualitatively and see what that looks like. So in the top figure right there, I've got two sources that are 6 wavelengths apart. So remember these little wavelets right here, these curved wavelets, these lines represent the leading edge of those wavelets. So there's 1 wavelength, 2 wavelengths, 3, 4, 5, 6 wavelengths apart. This is a point right in the middle of those two. So I'm going to draw points on there that represent constructive interference. Okay, so I'm going to draw 5 lines that represent constructive interference when the spacing, remember this is D, and right now it's showing D is equal to 6 wavelengths. Down here at the bottom, this figure is D equals only 3 wavelengths. So what we'll do is we'll draw 5 lines of constructive interference at the top in the top figure. We'll draw 5 lines of constructive interference in the bottom figure, and we're going to see how the D, we'll call it 1 up above, being twice as big as D2, we're going to see how that affects Y. So how is Y going to be affected? Well, you might be able to predict based on our equation on the previous page, if we change D a certain way, what's going to happen to Y, but let's see what happens qualitatively, all right? So I'm going to pick a line right here, and I'm going to start here. I'm going to draw a line right through all the intersecting wave points right there, all the wavelet crests. You can see 2 crests intersect here, 2 crests intersect here, and so on. So I've just drawn a line through those areas where 2 crests meet, and it's equidistant from each source, S1 and S2. It's the same distance to any point along that line because it's a bisector. So that's going to hit the screen, and there's going to be a bright spot. If the screen was along up here, you'd have a very bright spot right there. How about the next bright spot? Starting at that same point, let me come down here where all those points meet. So there's another bright spot right there. Oops. Yeah, about right there. Okay, let's draw a third one. And I'll draw a couple more. I'm running out of colors though, so I'm just going to go to black for the next one. And the next one. Okay, so those are my points. I'll put them in blue so you can kind of see them. Okay, so there's that distance. Y is this distance between here and here. So this would be 1 on the right side, 2 on the right side, 1 on the left side. So M1, M2 on the right side, M1, M2 on the left side. The central bright fringe would be where M equals 0. Okay, so now we've got narrower spacing, only 3 wavelengths down here at the bottom. So I'm down here. Let's see what those lines look like. Let me start with the central maximum. Now the center point here is 1.5 waves, so I have to kind of start right there. Let's pretend our, oops, sorry about that. Let's pretend our screen is right along here. So there's my central maximum. My next line, I'll make it blue. Looks like they're going to be spaced farther apart. I'm not exactly in between the two here. I'm in the wrong plane here because I moved things around. So I'm a little bit off with my drawing, but I think the gist of it is you're going to see what's happening here. Clearly it's the Y's are bigger. So when I space that out a little bit, the distance Y1, I'm going to highlight these now. I'll do it in yellow. Y1 for up here at the top is smaller than Y1 down here at the bottom, the spacing between the central maximum and the first maxima to one side. So what we just determined qualitatively is that Y1 is smaller than Y2. So when the distance decreases, the spacing increases. Let's see if that's true with the equation. When I write out this equation, let's see if it's consistent. When D increases, if I hold everything else constant, same wavelength, the wavelengths are the same. I'm measuring the distance to the first bright spot, so M stays the same. The distance between the screen and the sources, L, is the same. So the only thing I'm changing are D and Y. They look like they have an inverse relationship. So as D increases, so I went from, I'm sorry, D decreased, didn't it? As D went down in D2, Y should have gone up, and in fact it did. Y1 was a longer distance here than the first maxima in the bottom figure was farther away from the central maximum than the top. So it works out qualitatively. Quickly on the next page, we'll look at what wavelength does. Okay, so let's check out when we double the wavelength or make the wavelength bigger. Here's my source 1 over here. Here's my source 2 over here. Let's draw the first few. This is 3 wavelength spacing. So this is similar to the bottom figure on the last page. I think the scale's the same. Scale better be the same or else we're in trouble. Looks like our spacing for the first fringe is increasing. So M lambda over D equals Y over L. So my spacing here from the central maximum, this is 0, this is 1 on the left, this is 1 on the right. It looks like as wavelength goes up, so does the spacing. That's what we're seeing in here. So longer wavelength from here to here. This is a bigger wavelength than we saw on the previous slide. So that's consistent with what we would expect. So it's important for you to understand the relationship between wavelength and fringe spacing, like it is shown in this slide, and also the relationship between the distance between the slits D and the fringe spacing. So we've kind of illustrated that qualitatively. I hope that makes sense to you. Let's look at a problem here that quantitatively explores the phenomena with sound. So this is going to be more of a quantitative problem, but it's kind of an interesting one. It says there's two speakers. So this is a wave phenomena, first of all. This is not just a light phenomena, that light gets bright and dark. I think from the ALG problems you did last week, you saw that you also have sound being a longitudinal wave can also exhibit the principle of superposition, where you've got two crests or two troughs that occupy the same space at the same time and constructively interfere, or total destructive interference if they're 180 degrees out of phase. Either way, you can have an interference with waves and sound just like you do in light. So here's a problem where you've got two speakers that they're in phase, which is a very important aspect of these types of problems. They're in phase, 170 hertz frequency. I show that right here. And I know the speed of sound roughly in air is 340 meters per second. They don't tell you that, but you need to know that to be able to solve this problem. Can he do it? Can he do it? As you notice there, he's down here. 10 meters away from speaker A. Give us three distances that you could move speaker B to. So I've got to move speaker B around here to provide destructive interference to Ken if he stays 10 meters away from speaker A. So the conditions for destructive interference, and I'm assuming that they mean total destructive interference here. When they say destructive interference, I'm assuming that means total destructive interference. So they want it to be exactly 180 degrees out of phase when a wave from a crest from speaker A gets to Ken down here, that another wave from speaker B is 180 degrees out of phase when it reaches Ken. So the way that's going to happen is you're going to have a distance. We'll call this distance here S1, the 10 meter distance, and then we'll pick a random distance here for speaker B, and so let's keep him where it's at right now. We'll call this S2. So we want the difference in those two distances from source 1 to Ken and to source 2 from source 2 to Ken. Source 2 is bigger, so I'm going to subtract source 1 from source 2. We want that to be a multiple of half wavelengths. So M could be 1. M can't be 2, because if M is 2, then 2 divided by 2 is 1. So M can only be odds up here. Okay? So let's start with the first possible area of destructive interference when M is equal to 1. So I'm going to start with that. When M is equal to 1, this is equal to lambda over 2. The difference in the distances between those two sources and can he do it is lambda over 2. But we got to figure out what lambda is for a 170 hertz tone in air with 340 meters per second velocity. We're going to have to use our wave equation. So lambda is V over F. Lambda is 2 meters, because that's 340 over 170. Okay, so if lambda is 2 meters, then 2 over 2 is the difference has to be 1 meter. So this would have to be 11 meters here. That is 10 meters, so we could put speaker B 11 meters away. Or the next possible location would be if we chose M to be 3. So the difference between the two sources is 3/2 of a wavelength, which would be 3 times 2 over 2, or 3 meters away. So this could be 13 meters, and you can guess by the pattern, when M is 5, the next distance would be 15 meters. So that would be for total destructive interference. We could place speaker B 11, 13, or 15 meters away, and can he do it would hear no sound at all if these things were perfectly in phase. This wouldn't work with just any music. This would have to be a pure tone, just a frequency of 170 hertz, a single note, and the two speakers would have to be perfectly in phase for the distance that we calculated to work out. If they were out of phase, 180 degrees out of phase, we could accommodate that. We could find distances where out of phase tones would produce total destructive interference, but we would have to change our calculation slightly. So out of phase would still work if they were perfectly out of phase. It would just be total destructive interference at different distances. All right, we're going to swap now. We're going to talk about a new idea, which it's the same concept of wave interference, but we're going to talk about it in the context of gratings. And you might ask, what's a grating? A grating is a slide with more than just two slits on it. A grating is a slide with many, many, many tiny little lines cut into it, like almost like you paint a slide and you take a razor blade, even thinner than a razor blade, and you etch tiny lines, multiple lines in it. Instead of just two, you've got multiple slits, we'll call them. So here's what we've already seen. I'm over on the right-hand side right now in these pictures, a series of vertical pictures with two slits. We've already seen, this image right here. What if you do three slits? How does that change? So on the next slide down, we've got three slits. And the way that changes is we actually see that the spacing is the same. So the center of these slits is still in the same place, but the slits are a little more defined and a little bit brighter. And as we go to 4 slits and 5 slits, the location of the maxima don't change, but they get brighter. And the reason they get brighter is instead of having just 2 slits for light to get through, now you've got 3 slits. So it makes sense that with 50% more space for light to get through, I've added another slit in the second one here with 3 slits. I'm going to have 1.5 times as much light getting to the screen, so it's going to be brighter. Another property of more slits is the maxima gets really tightly defined. So you can see here, these are getting more tightly defined as you go in this direction. Each additional slit sharpens up the interference pattern in the maxima. And that's a complicated property of the interference pattern. So we won't get into the details of why it gets sharper. Just know that it does get sharper as you add more slits. So a grating is a slide, and we would do this in class if we were able to. Unfortunately, we can't because we aren't in school, but I would actually do an experiment. We have some gratings in class with different color lasers, and we would see what happens to this spacing with different color lasers, different wavelengths of light. But the same exact relationship applies that we've already learned about with Young's double slit experiment. So M can be anywhere from 0 to 1, 2, or 3. The plus or minus just means on which side of the maxima it's going to be. We could call X positive to the right. So all the left maxima would be negative maxima. Doesn't mean they're any different. They're just on the opposite side of the central maxima. So a grating is actually a really useful tool to analyze light coming from different sources to try and understand the wavelength of the light that is coming in. So it's a really interesting way. It makes it easier to analyze because it's such a sharp, well-defined interference pattern. Just note here, this is one of those tips. Gratings are labeled in terms of slits per millimeter. So D is millimeters, usually the spacing D between slits. When we've talked about Young's double slit experiment, we've measured those in millimeters on the previous video. That's millimeters between slits. So 1 over D would be slits per millimeter. So when you buy a grating, when you order a grating, they come in the number of slits per millimeter. So if a grating has 1,000 slits per millimeter, you can figure out what the spacing is by taking the inverse of that. So we'll talk about that in the next example. So this is more of a quantitative example here. Qualitative example. This is what I would do in class if we were in school. And so I've got a red laser. You guys have seen the red laser. You've seen the green laser. Some of you guys have seen the violet laser in class. Let's pretend I've got a slide right here. And my slide has, I only show 2 slits here, but with a grating it would be many, many, many slits. I can't possibly draw them thin enough. And you'd shine the laser at this. And I've shown as a baseline here the red laser. So let's pretend I've got the red laser that creates this pattern up here. And here's my central maxima right here. Here's my one on the negative one, I guess you call it, on the left, positive one on the right, and so on. So there's my spacing Y1 using the red laser. It's important you guys remember that wavelengths of light go from 400 nanometers, as I talked about in the last screencast, to 700 nanometers. Red's down there, violet's over here. Okay, so longer wavelength, red, shorter wavelength, violet. The way I think about that and remember it is ultraviolet is even shorter than the violet. Infrared is even longer than the red. We can't see these, but those are the electromagnetic waves that are just beyond the visible spectrum on each side. 400 being the higher frequency, shorter wavelength. So let's say I go to a green laser. So if red is the shortest and red is the longest, violet's the shortest, green must be somewhere in the middle here. So go to Young's double slit experiment or equation. If I go from a red laser to a green laser, what do you expect to happen to this fringe spacing up here? Are they going to be further spaced out, or are they going to be closer together? Think about that for a second. Okay, if you made a prediction, let's say I go to a green laser and I shine one of my green lasers through the same exact grating, and I haven't changed any of these other parameters. The only thing I'm changing is this, and I'm trying to make a prediction about that. The length to the screen is the same. The grating, the spacing between the slits is the same, and I'm going to measure the distance between the central and the first. So what happens when I decrease? This is the longest wavelength, long. This is shorter here. So I've gone down in wavelength. I would expect the spacing to actually decrease. So they're going to be a little bit closer in here. You can guess what's going to happen when I go to violet, which is the shortest. These are going to be in even tighter. So these are going to come in here. The central max will be in the same place, but when we do this in class on the blackboard, on the whiteboard up front, they actually move in closer. So that's what a grating is. I hope that makes sense to you, and we'll talk a little bit more about electromagnetic waves and how wavelength and frequency vary when they go into different mediums on the next screencast. So I hope you guys have a good week. Stay safe and stay close to home.